to be looking at confidence intervals for uh, population proportions. What we want to think about that what we're looking at is relative frequencies, percents, and remember binomial probabilities where there's a percent success and that there would be a percent failure, which is always 1 minus p, right? Because p and q have to add to 100%. Remember, chance of rain is 70%, chance of no rain is 30%. This is what we call a failure, or true or false, something along those lines. So, but what we're working with is a percent rather than a mean, rather than an average. We're going to see that it's very, very similar to what we've been working with, except it has a few different formulas involved. Again, the calculator is going to take us through the process very nicely all the way through as we go. So we're going to find a point estimate. We'll see that's pretty straightforward to do. Remember, our point estimate in this case is not a mean, it's going to be a percentage. We're going to construct an interval. So say our percentages we've come up with is say 70%. And maybe our confidence intervals is going to be, we calculate an error and then we add and subtract that. Let's say that comes up at 4%. So we add 4% and we get 74%. We subtract 4% and we get 66%. And that is our confidence interval. We're estimating that it's about 70% with an error plus or minus 4%. We will also see that that error that we're trying to maintain or get it below a particular error will determine the sample size. So we will see a calculation how we can make sure our sample is big enough so that our error is small enough. Okay. Large enough sample size, the larger the sample size, we can reduce the margin of error, because that's part of the calculation. All right, so let's get right into it, and here we go. So what's a population proportion? Well, population proportion is the probability of success, just like we talked about. We use p, it's a percent or a decimal, and it's the probability of success. Now, we may have more than one proportion. We'll look at those in a little bit. What we do, though, is remember populations typically are so large that we can't get all that data, so we go and get a sample. We get an estimate for p, point estimate, like I said, a particular value, by looking at the sample. And when we look at the sample, what we're going to invent a new symbol here. We'll call this p hat. This little thing is a hat. And x comes from the sample and n comes from the sample. X is the number of successes in the sample, the number of times, the number of days it rained, or whatever we're talking about. X is that number of successes. And then, n is the sample size. So we just do a division, which gives us a percentage, right? And then we also can tell the percent of failures, or the proportion of failures, which will be q hat. And we can always get that by taking 1 minus p hat. So 100% minus whatever that is. So, if p hat were equal to 70%, if this ends up becoming 70%, then q hat is going to be 100% minus 70%, 30%. Okay, a lot of times we can do this in our head. The thing is, it throws us off sometimes if we do it with decimals. Sometimes we get 1 minus 0.7 seems like such a harder thing to do, but that's just going to be 0.3. So think in terms of percentages. Oftentimes makes it easier. So let's look at an example. How would we go about this one? We've got a survey, which is from a sample of the population, right? 540 US adults. That's the sample size. 378 said they plan on traveling this summer. That's the number of successes, the number of people who are going to travel. Find a point estimate for the population proportion. So that population point estimate is going to be p hat. We're going to take 378 divided by 540. We're always going to get a number less than 1, less than 100%, because the sample size, unless could get 1 itself if everybody was going to travel. I'm going to show you that we don't have to go calculate it with the standard part of the calculator. We can actually come to inference, and this is one of the first things that it's going to do for us. I'm going to have to back up here. So what we're working on from inference, step by step, we're doing intervals, confidence intervals. This time we're going to do one proportion, and notice it's going to be a z interval, not the one mean where we have two choices, either a t or a z interval. We've already done these. We're now doing the one proportion, and all we'll be using is a z interval here. Because we're going to see that the point estimate that from the sample, if the sample's large enough, it's going to be approximately normal. So this is where we put our x value, so 378, and our sample size, 540. And then we put our confidence interval. Well, they haven't mentioned a confidence interval, so we'll just leave it at 0.95 for now. If we later on get this and they change it on us, we will change that. Notice it has calculated p hat for us. It took 378 divided by 540, and so it tells us it's 0.7. So why not just use this part of the calculator, which is going to calculate the value for us. It's also given us everything we need to do all the other calculations, but it's actually calculated these other things that we need. It's given us our margin of error, our plus or minus right here. But we're going to see, we'll look at the formulas, but it's already taken care of it for us. All we had to do is put in x divided by n. Incidentally, if they give us the p, well, we'll maybe look at that while we get into the homework. There's a way to figure out from the sample size what x is, because this calculator does not allow us to directly enter p hat. It has to calculate it. So that's the first step. And then what we're going to see is then we've got this calculation for the error, which the calculator's already jumped ahead and done for us. So it didn't give us q hat, but that's what we would have needed to do. Calculate q hat, multiply this, divide by n, take its square root, and then multiply by the critical value, which is given us here. So we've got the ability to carry this out and see that if we did this calculation, we would get a margin of error of 0.038. That's what we end up with. And then we would take our p hat that we came up with. Remember, in both cases, it was 0.7. And we would see that we could use that to estimate the population proportion. So this p without the hat, this is for the population. This p hat, this comes from the sample. This one comes from the sample. It's the same one. P hat is p hat, but just want to emphasize we're using the sample. We're calculating a margin of error plus or minus to get at what the population is. This is our confidence interval. And again, it's the idea that if we repeat this process a large number of times, we would have a 95% confidence that the population proportion would be within this interval. Okay. So here's the things that we need to do. First, we need to verify our statistics, which we did, x and n. We need to get those. We can then calculate the point estimate, which the calculator, once we put those in, has done for us. One thing we haven't talked about, but this is to ensure that the distribution would be something that's normal, so we can use z, is that when we take the sample size times p hat and q hat, they both have to be larger than 5. So we could just do this on the side. If they're not larger than 5, then we can't do any of this, so we would back off. Okay, what you're going to see in the homework, most of them are going to be much more in larger than 5. So again, what we could have done here with the 540 is tested out 540 times, we came up with 0.7. Yeah, that's much larger than 5. 100 would give you 70, so it's going to be there. Q hat is 0.3, so 0.3 times 540. And again, you could do this. That's much larger than 5. A third, you could think of 30% of 540. Well, yeah, that's going to be much larger than 5. That's all we got to do. It's just kind of a check. So yeah, we can do this. We then find the critical value. Again, you could use the table, but for us, the calculator has done that for us. Since the calculator is handling the calculations, we actually don't need this. The calculator just displays to us what it's showing its work. It's letting us know the process. So we could come back here and do this as we need it. And then the final process is to use that formula. And again, we will use this at the end, but that gives us our margin of error. Okay, so E, or in this case, we're going to see it on our calculator as ME, margin of error. And then you add and subtract that to the proportion, right, to get our left and right endpoints. And that's done for us, erase that part, in the calculator as we go to the next step. It has added and subtracted that margin of error, again, about 4%, right, 0.03865. It's added it, so we get 0.73865. It's subtracted it, 0.6613. So we have our plus or minus, we have our confidence interval. That what this is saying is that we are 95% confident the population proportion is between 66% and almost 74. We just kind of round those, right? And so now we're ready to look at a couple examples. Well, actually, we've already done this, haven't we? We used the data in example 1 to construct a 95% confidence interval. And it was really very straightforward. All we had to do is enter those two values, go to the next, see what the results were, and then we are able to verify, yes, the margin of error is being added or subtracted from the point estimate. Here we are, we're done. And so, yeah, we could just put that, the confidence interval is going to be 0.6613 all the way to 0.7387. Sometimes it wants it as a plus or minus. If we, the confidence interval is 0.7 plus or minus 0.38. 0.0387. Rounded to 4 decimal places. And that's it. We've done it. So we're going to keep moving forward here. And we will see that we can do it for something else. So again, to do this, what we need to know is a survey. We need to identify our sample size, 800. We've been given a confidence interval of 99%. So we can back up our calculator here, doing one proportion. And then this is where it's a little tricky. Okay. For the population proportion of U.S. adults who prefer to get their news from television. Television, that's 35%. Notice they give us really p-hat, it's 0.35. But the calculator does not give us a place to put in 0.35. So what do? Well, this is where we have to do a little bit of calculating on our own. We are going to take that 0.35, 35% of 800. We're going to multiply those two together, and that would tell us how many people prefer television. Okay, so what we'll do, let's see, why don't they just give us a p-hat here? I don't know. But the only way they give us is we have to have the number of successes, not the percent of successes. But instead of going back to the full calculator, let's just put this in, 0.35 times 800. Notice it tells us that's 280 people. And then we have our sample size of 800. So pretty straightforward. And then we have our confidence interval. 99% is going to be 0.99. And now we are pretty much done as we go forward. We've got our sample size is 0.35, but actually we knew that, right? Our Z critical value for a 99% is 2.57. That will get used in the calculation, and we may need that later on. We can see where that is. And then we've got our margin error is a little over 4%, right? 0.0434. See, go to 4 decimal places. Okay, so we can construct that confidence interval. Let's go one more screen. We can write that out as confidence interval of 0.3066, so about 30.66%, all the way to about 39.34, about 39%, right? So somewhere between 30 and 39%, right in there. Or we could list it as 0.35 plus or minus 0.0434. 4 decimal places. We've constructed our confidence interval. Okay, so that's how it works if we aren't given the number of successes, but the percentage of successes. Just kind of plug it in on that first screen. It will carry out the calculation. Again, I just put in the 0.35, 35% times 800, and it will calculate it and put it right there for me. Kind of nice. The last thing we have left to do is how do we know if our sample size is big enough to have an error size that we want, a small enough error size. So as n gets bigger, the error will get smaller. So what we do is we start out with this formula. Again, we won't have to do this all the time. We're going to do the algebra one time. So we're going to solve this for n, right? We want to get n by itself. So we would divide both sides by z sub c, right? That cancels out. And then we have e over z sub c is equal to the square root of p hat q hat over n. This is why we have to understand these things. We would square both sides. So that takes care of that. So we end up with, see, I don't know if, yeah, I think I just go down here. So we get E over Z. Okay, we'll find these. These will be given to us squared. These guys sort of cancel. And you get P hat, Q hat over N. I would multiply both sides by N. Get rid of the n there, we'll have it here, and then multiply by the reciprocal of this. So you're going to multiply, and I'm almost to where I've got it. So you take E over Z C squared times Z sub C over E squared. These will cancel each other out, right, or give us a value of 1. And so that gives us our final formula. And I know I was running into problems here. Get kind of rid of this stuff. And we're going to have P hat, Q hat multiplied. And notice how this is sort of the reciprocal of what we started with. It's this Z, C over C. So this is the formula we're going to want written in our notes. This is what we're going to use to calculate. Let me get rid of some of these. I just want you to see the process. We're not going to do it multiple times because, again, we just use formulas because there's so many different formulas. Yeah, we could try to memorize these. If you were a statistician that were doing these on a daily basis or weekly basis, you would come to remember these and do it. But what we want you to be able to do is be able to do multiple ones of these and be able to go forward. Okay, so remember, if n is a decimal, you round it up to the next, because it has to be a whole number. Sample size has to be a whole number. Uh, if they don't give the proportion values, because sometimes that happens, they don't give us P and Q, then we can use an estimate. We say basically, let's start with 50-50. It gives us an estimate of what our sample size should be. We go out and do it. We might have to do it a couple times, but if they don't give it to us, this is the best place to start, kind of in the middle, and do sort of a guess and check. So we're going to look at two questions, one where they give it to us, one where they don't, and see how we will be able to calculate the sample size. Okay. So here we are. You're running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3%. So the boss has said, margin of error no bigger than 3%, right? Find the minimum sample size needed. First, when we have no preliminary estimate is available. Well, in that case, remember, we're going to just make an assumption that p hat is 0.5 and q hat is 0.5, right? 0.5 plus 0.5 is 1. And so we go about and put in our values here that our sample size has to be 0.5 times 0.5. That's a p hat, q hat. Those are coming from right here. Z critical value, since we want 95% confidence, it's still a Z value. You may remember that's 1.96, but if you don't, what you can do is right here in the calculator, before we start doing all this stuff, we can put in a 0.95. Doesn't matter what these values are up there, it's going to give us that Z critical value of 1.96, right? It's always going to be the same for a 95% confidence interval. So then we've got 1.96 divided by the margin of error, which is 3%. As a decimal, that's going to be 0.03. So that's our margin of error. Margin of error, 0.03. And then we're going to square that, and that will give us our value. So this time we will go back to the main regular calculator and just calculate it out. 0.5 times 0.5 times parentheses 1.96 divided by 0.03 squared. And you could go an exponent here, but you could just do the square. And what it tells us, we need 1,068, because we're going to go up to the next highest number. Because otherwise, 1,067 would just be a little bit not quite enough. Okay, rounded, not necessarily, I don't call it rounding because you wouldn't round this up, but go to the next highest integer value. Okay, and we'll just run through this one more time. And that's the example where they will actually give us what p hat is. So somehow they had an estimate, maybe from the last surveys that went out. And so again, we do the same thing. We start with the same formula, but this time we have our p hat. So we're going to have 0.31 for p hat, and that's going to get multiplied by q hat, which is 1 minus 0.31. So that's going to be 0.69. Okay, so we have to do that math a little on our own, or you could just enter it in that way. You could enter 1 minus 0.13. And then we're going to have, it's a 95% confidence interval, same confidence interval, so it's 1.96. Again, we could look that up on the calculator if needed. Margin of error is still 3%, so 0.03. We square it. And now let's see how many, what the sample size is that we would need. 0.31 times 0.69 times parentheses 1.96 divided by 0.03 squared. Oops, it's the wrong place to put the squared. Arrow over, pay attention. Let's square it. And then we see we only now need 900. Now see, even if it's a 0.02, it's 914 is what we want to report this as. Always go up to the next highest number, 914 sample size. So that would be n. And now we're ready to work on the homework. Thank you so much.